Hello there. Welcome to the engineering mechanics tutorials. In this video lectures, we are trying to learn what is the moment of inertia for a rectangle lamina. As we know that the moment of inertia here we are taking for the area. We know that the resistance is developing for the bending forces. For suppose a body is going to be subjected to the bending forces. Suppose this member is going to be, this is going to be the circular objects, it is subjected to this, the bending forces in this direction. So then what will happen? The cross-section area is going to be trying to resist the bending forces. It's most of the time we are dealing this one, either the deformation of the member or the deflection of the members we are going to be calculating by using the area moment of the inertia. In this diagram, we had a rectangle lamina is available. So the rectangle lamina, the base is going to be the B and the height we are going to be measuring with the H. As we know that the center of gravity we already calculated in the last video lectures, that the centroid we are going to be calling, the centroid of this rectangle lamina is, that is going to be XC comma YC is equal to, how much we are going to be getting? That's going to be B by 2 comma H by 2. On that basis we are going to be calculating the centroid. So once we are going to be calculating the centroid, and we need to be calculate the moment of inertia with respect to the centroid. So that means I am going to be taking the axis over here. This is going to be your X and this is going to be your Y axis. Can you see the centroid? That means your observation axis is passing through the centroid, that as a XX as well as the YY. So now I want to find out the moment of inertia with respect to the X axis. It means that with respect to this axis, how this area is going to be distributing. Can you see here that area is going to be, when it is going to be subjected to the certain type of the forces, and how this area is going to be resisting the change. That's we need to be calculate here. So that I'm going to be taking the moment of inertia of this object with respect to the X axis. That means on this axis, that is equal to, the formula is going to be integral y square dA formula we are using. In this equation, we need to be find out the dA over here. To this one, we need to be first to find out the elemental strip. So the elemental strip we are taking parallel to the x-axis. So that's going to be your x-axis I have taken. So this is going to be your the elemental strip. It has a thickness of dy thickness I have taken. At the same time, the width of this one is going to be same as your base. So the dA is equal to, that's going to be elemental area I am going to be taking. So that's going to be elemental area dA is equal to, what is the formula we had? That's going to be B into dy we are getting. Right? At the same time, it is going to be located at a distance of y from your observation axis to the elemental strip. Can you see the elemental strip we have taken above that one? It means that the total height is going to be the H we have taken. So that y is going to be distributing above that reference line and the below the reference line. That's why I'm going to be calling here is going to be minus H by 2 and this is going to be the plus H by 2, two intervals I have taken. So now I'm going to be finding that moment of inertia of this elemental strip. So that equation I'm going to be writing over here, Ixx is equal to the integral minus H by 2 and here is the H by 2 plus. And this is going to be your y square, and similarly dA I am going to be replacing with the elemental strip, that's going to be B into dy. So once I am going to be substituted in this equation, further the thing is that we need to be simplify that, so that we can find out the resistance area for the bending forces, we will get it. So that means B is going to be constant in this equation, that's the B I am going to be taking out, and integral minus H by 2 and here is the plus H by 2, that's going to be y square dy we will get it. So once we took out the constants and the variable parameters we are going to be integrating. So from this one I am going to be getting B into, that's going to be integral y cube by 3 we will get it. That's going to be y square dy integration we are getting y cube by 3. So the intervals are going to be varying H by 2 minus H by 2. If I am going to be substituting these intervals in this equation, I am going to be getting here, what is the value we are going to be getting? So there we can see here, so that the same equations I am going to be considering over here, that's going to be Ixx is equal to B into, so then the first interval I am going to be taking here is the plus 1. So that's going to be H cube and this is going to be 3 times we have to multiply, and 2, 4, 8, 3 into 8. So that's going to be 3 into 8 minus of minus h by 2. So here is going to be the whole cube by 3 we are getting. Once if I am going to be simplifying this equation, so again I am going to be simplifying here. So that's Ixx is equal to b into h cube by 24 minus minus will become, here is going to be plus h cube by 24 I am going to be getting. So then in this case LCM is going to be the constant, and then I am going to be finding over here. So that's going to be Ixx is equal to b into 2h cube by 24 I will get it. So then the 2 is going to be dividing with the 12 times. So then Ixx is equal to bh cube by 12 I got it. So this way, this is the amount of the area where it is going to be resisting for the bending forces. Okay, so this is going to be Ixx is equal to b into h cube by 12, we got it. I hope you are able to understand how to find out the moment of inertia of an area with respect to the centroid. And this one we have taken the Ixx. Now we are trying to calculate for the Iy. If you want to calculate the Iy, we need to take the vertical strip over here so that we can calculate that part. Now we are going to be find out the moment of inertia with respect to the y-axis. Already we told that it is going to be passing to the centroid. So this is going to be your y-axis, right? And this is going to be your x-axis. Already we have calculated Ixx is equal to bh cube by 12, we have derived the equation. Now I want to find out the Iy, that is equal to integral x square dA. To satisfy these conditions, the first I am going to be taking the, with respect to this axis, how the area is going to be distributed and how it is applying the resistance to the bending force. So then I am going to be talking about the dA here. The dA is equal to, I am going to be taking the one elemental strip which is parallel to your observation axis. Here your observation axis is going to be your Iyy. So this is going to be your observation axis and this is going to be your dx. So there we can see here, and this is going to, the elemental strip is going to be the dx, and it is located at a distance of x distance from the y axis we have taken. Now I am going to be finding the dA, the elemental area. So here that elemental area is equal to, now in this case it was spread along the length direction, and this is going to be the dx, that I am going to be taking h into dx I am going to be taking. Can you see here the x is moving from the centroid towards the right side and towards the left side. It means that we are using the b coordinates here. So that's going to be, this towards the left side is going to be minus b by 2, and this is going to be b by 2 I am going to be taking. So these limits I am going to be substituting in our equation. That's going to be Iyy is equal to integral, here is going to be minus b by 2 and here is the plus b by 2, and x square I am going to be taking, that is the element is located at a distance of x, and then the dA I am going to be writing h into dx. Now we are going to be trying to take the constant outside, so that I am going to be getting here. So that is equal to, h is going to be the constant, it is not going to be varying. So then your integration is going to be minus b by 2 here and plus b by 2, the limits x square dx. And further simplification of this equation, h is equal to x cube by 3 into b by 2 minus b by 2 I am going to be getting. So then I am going to be substituting these limits in this equation so that I can, x is equal to integral. So that means we are substituting the b by 2 in this equation. That's going to be b by 2 whole cube into 1 by 3, minus into minus will become plus here. So that's going to be b by 2 whole cube 1 by 3 I am getting. So once if I am going to be simplifying that equation, so we are going to be getting, so that is equal to, that's going to be Iyy is equal to, so this is going to be h, this is going to be your b cube, and the 2 is going to be 8 into 3 24 plus b cube by 24 we are going to be getting after the simplification of this one. So then LCM we are going to be taking here for the simplification. That's going to be 2b cube by 24. Right? So then Iyy is equal to 2 is going to be here divided by 12 we are going to be taking. That's going to be hb cube by 12. We got it. So can you see Ixx is equal to bh cube by 12. Iyy is equal to hb cube by 12. So now this is the amount of the area where it is going to be start to show the resistance that we will see numerically. So here I am going to be taking the dimensions of the A and B. Suppose if B is equal to 2 and then H is equal to 1 meters I have taken, either centimeters or millimeters or meters also we can take it. For the time being I have taken this one. So then what will happen? Ixx is equal to, what is the formula? B is equal to 2 and H is equal to 1 cube by 12 we are getting. So then from this Ixx is equal to, I am getting 1 by 6 meter to the power of 4 I am going to be getting. So that means 1 by 6 only we are getting here. Suppose Iyy is equal to, I am substituting in this equation 1 into 2 to the power of 3 by 12. So in this equation Iyy is equal to, the 2 means 8 by 12 we are getting. So 8 by 12 means here this is going to be 4 times, this is going to be 6 times, this is the 2 times and this is the 3. That means the finally we are getting the 3 times. So can you see which area is going to be the, we are getting the maximum. Suppose you can see here, that's going to be Ixx is equal to 1 by 6 and Iyy is equal to 2 by 3. In this case, it is going to be very clear to us. So Iyy has the maximum area compared to your Ixx. So then the resistance is going to be developing with respect to the y-axis. That means this area is going to be, with respect to this area is going to be applying the more resistance. Ixx is going to means in this direction. Vertical direction is going to be less compared to the horizontal direction. I hope you are able to understand this concept and how we are going to be calculating the moment of inertia for a rectangle lamina. Suppose we have taken the centroid is going to be your observation point. So then if I am going to be taking at the base, so then we will get the another equation over there. So then this way we are going to be calculating. So still if you feel any confusion, then please put in the comment section so that I can reach you out. So thank you.